we've started looking at this concept of percent composition, which is like any other percent, a part divided by the whole, but now we're applying it to chemistry. In the last example, where we had this mercury oxide compound, and they started with 14.2 grams and heated it in the lab and found that there were 13.2 grams of mercury remaining, we were able to use lab data to figure out like an experimental percent mercury and percent oxygen in the original mercury oxide compound. But we can also do that with theoretical data. And so here we can do percent mass in a compound by looking at molar masses. And we would call it like a theoretical. Percent composition. Sometimes in the lab, we've got data that's a little flawed because of errors. And maybe I didn't measure something correctly, or I spilled something, and so my measured numbers aren't perfect. And so then maybe my percent composition isn't 100% accurate. But if I want to get an accurate percent composition of an element in a compound, we would use molar masses, theoretical molar masses off the periodic table. Theoretical just means like the true accepted percent composition of all elements in a compound. Now there's this law called the law of constant composition that just says that for a particular compound, you've got to have the same elements always in the same ratios in order to have the properties of that compound. And so any molecule of water has to have the elements hydrogen and oxygen, 1 oxygen, 2 hydrogen. Same elements, same ratios, in order to have all the properties of water. Which then I could use theoretical molar masses to also do a percent composition. And that's what they're kind of showing us down in step 3. Where let's say I look at the molar masses on the periodic table, and I kind of add them up, just like how we were adding up to find molar mass of a compound. And so oxygen's mass is about 16 grams per mole, and the hydrogens are each pretty close to 1. So now what if we did a percent composition using these molar masses, where the total mass of hydrogen in a water molecule would be 2 grams per mole, and the mass of a water molecule is 18 grams per mole. You could do a percent composition using molar masses, and we get about 11% hydrogen by mass. We could do the same thing with the molar mass of oxygen. There's 1 oxygen for 16 grams divided by the total mass of a water molecule, molar mass of 18 grams, and we get about 89% oxygen. Now these would be theoretical percent compositions, that any sample of water that has hydrogen and oxygen in a 2-to-1 ratio should end up being 11% hydrogen and 89% oxygen by mass. That's the true accepted composition of a water molecule. And so again, it's like the same concept, but we can do this type of a calculation with lab data, or we can do it with theoretical data off the periodic table. So for example, here's 22. There is something called heavy water. Heavy water just has a different isotope of hydrogen. Most hydrogen is hydrogen mass 1, atomic number 1. So you kind of remember these symbols that we used way back in the day, where the top number was the atomic number, and then on the bottom we had the mass. Now hydrogen is normally a really simple atom in that it's got 1 proton. Okay, so there's 1 proton. It's neutral, so there's also got to be 1 electron. But we said the mass of a proton is like 1 AMU, and electrons are so tiny we don't even count them. So if the mass of this thing is just 1, there are usually no neutrons. It's a really simple atom. One proton, one electron, done. But there are other isotopes of hydrogen. They're just not as stable and not very abundant. But there's an isotope called deuterium. Deuterium symbol looks like this. Oh, so the atomic number is still 1, which means that there's still one proton. It still has to be neutral, so there's one electron. But this time the mass is 2. So that means that there's one neutral neutron. So they call it heavy water just because the hydrogen is this heavier isotope, deuterium. Okay, so they want us to sketch the percent composition pie chart for heavy water. All right, so here's what this would look like. I'm going to do something where I have percent hydrogen. In heavy water, it's going to be the mass of hydrogen divided by the mass of the water. And again, this is going to be for the heavy form of water. Heavy water means this, where the mass is 2, twice the molar mass of regular hydrogen. Okay, so in water there's 2 hydrogen atoms, but now if it's heavy water, their mass would each be 2. So if I were finding the molar mass of heavy water, I would say hydrogen's mass is 2 grams per mole. There are 2. And oxygen's mass, let's say we leave it as like a whole number. It's really close anyway. 16 grams per mole times 1. Ah, okay, so this is 16 and 4 for 20. Whereas normal water has a mass of 18 grams per mole. Because normally hydrogen's molar mass is 1, oxygen is 16. So that heavy form of water adds a little bit of mass coming from the hydrogens. Okay, so now I can say, well, the total mass of hydrogen, there's 2 hydrogen, they each have a molar mass of 2 grams per mole. So that would give me 4 grams of hydrogen, and the whole compound has a mass of 20 grams. Multiply it by 100 to get a percent, and we're all good. 4 divided by 20 should be about 20%, right? So we'd say it's about 20% hydrogen. Then obviously we could do the same thing with the oxygen. It would be the 16 grams of oxygen divided by 20 grams of heavy water times 100 to make it a percent. And just to confirm that I've got this right, what do you know? I'm looking at 80%. So I know I did it right if my percent oxygen and my percent hydrogen add up to 100. And they do. So from here, if they wanted me to set up a pie graph, I guess we could, but it would be kind of an estimate in that, let's see if I can set up a pie graph. We'll get a little more space in here. All right, so if about 80% of this thing is oxygen, oh brother, if I were to divide this in 5, it would maybe be like something like that. But this would be 80% oxygen by mass and maybe about 20% hydrogen by mass. That's a very rough estimate of a pie graph, but I think we get the idea that this percent composition can be done with lab data or theoretical molar masses. So then any sample of water, heavy water in this case, should be 80% oxygen and 20% hydrogen by mass. Regular water would have this composition. Normally 89% oxygen and 11% hydrogen by mass.